Good morning, one and all. This is Harita K from Government College of Technology, Coimbatore, Department of Manufacturing Engineering. Today I am here to tell about my project phase 2 on the topic of optimization and simulation of gating design for the cast piston parking and spring sheet component under the guidance of Mr. R. Surendra, Assistant Professor, PG Manufacturing Engineering, Department of Mechanical Engineering. This is about an objective to analyze, study the process and method followed in the foundry, and also reduce the rejection rate by the optimizing the methoding and process parameter. Process parameters includes moisture content, sand or dryness and pressure and permeability level, and the amount of an additive like bentonite, kyolite, different type of sand moisture content has to be minimizing the processing, and also to improve the yield of the casting as well as the scrap utilization, and to improve the profit by reducing the sampling trials in production process. And introduction in there are n number of different advanced technologies in the metal casting had been developed, but the green sand casting process, one of the most widely used technique in the casting process today from the decade. And due to the low cost of the raw materials and in-time production process is also with respect to the size and composition of the component can be produced with the n number of lot in the production. So during the fast development in the automobile and also the machine tool industry, they are in need of the higher productivity. So time consumption is a major problem. So in order to reducing that, optimization techniques have been using like simulation software, 3D CAD, likewise a different n number of optimization methodings have been developed. So problem definition. For the foundry to run efficiently, the rejection rate must be lower than the 5%, but here it is around 10 to 20%. So the traditional method of trial and error method is using for methoding process and also analyzing the process parameter level, and time and the resource consumption is a major problem. So if we increase the time consumption, then the expenditure will also be higher. Then this is about a methodology, selection of the component, what kind of a component, whether it may be an automobile component or a non-auto component has to be selected, and study of the component, why, what kind of the problem it is attaining to face, whether it is kind of production process problem or due to the design problem, we need to analyze that. Then problem identification, and with respect to the problem identification, literature review has to be done with the and also the determination of the design process parameter. Then optimizing the methoding using the simulation software. Here the AutoCast X1 software, it is only using for the casting flow analysis process. We can find the defects like the shrinkage, the level of porosity, air fraction, then what kind of the temperature it attaining in between the material. With respect to the thickness level, we can slice it, and we can with respect to that we can measure the level of shrinkage up to the 0.01% of a level. Production is very optimizely we can predict from this. And finalization of the design, pattern making, trial and testing method, then validation of the result with respect to the metallurgical mechanical aspects I am taking, and result and discussion and conclusions. So this is about the literature review. Raghavendra Banchar is with respect to the optimization in the grain and sand casting for efficient and economical quality of the casting. Here the main area of the optimization in the grain sand casting is a production level, and with respect to the AutoCAD software, what kind of designing process can be used to stimulate and also reducing the level of the process parameter to avoid the defects. And Jadav MN says with respect to the gating design optimization with respect to the yield percentage. So we can compare with the existing gating system and modified gating system, what kind of the yield percentage which is efficiently we are attaining with respect to the directional flow of a material. So directional solidification is nothing but the variation of the speed and the flow of the metal will be in the same direction. So there will be a uniform grain size will be developing from the mold cavity towards throughout the material. So it will be very fine for the material to attain the strength. And ROKTL, this is analyzing the pump body casting using the process simulation technique. Here a proper design using the 3D CAD and also with the simulation techniques of an AutoCAD X1 software is used. So here what kind of an optimization with respect to the level of the gating design is modified and what kind of a yield is attaining when it should be a defect free casting, that is sound free casting should be attaining. Then Kiran R. Jadder, he is using with an aluminium alloy of series AA6063. So this is a rectangular component. With respect to the thickness, some kind of a solidification shrinkage will attain at the center point. So with respect to the changing the designing of gating system, and also with respect to the pressurized gating system or non-pressurized gating system, here 1:4:4 is a gating ratio for the non-pressurized gating of aluminium alloy. Hence why non-pressurized gating is using for the aluminium alloys, it is a non-ferrous material. So with respect to the non-ferrous, the composition, the level of each element with respect to the flowability and also the density, we are using the non-pressurized gating, and we can able to find the level of the shrinkage at the feeder and also inside the component can be corrected throughout the simulation technique. Then Ganesh B. Borikar will be saying with the same respect of an aluminium alloy of LM4 casting quality. Here the fine directional solidification has to be taking place, and instead of the top feeder, side feeders are used, and also with respect to the design of the component, whether it is a solid rectangular or it is a hollow cylindrical or the ring shaped component, how the designing gating should be minimizing with respect of the methoding. So that has to be analyzed. And software used as a design software is SolidWorks 2019, and simulation software is AutoCAD X1. This is a piston parking component to look as similar to the ring component, but the dia is about 706 at the top, bottom is 619, and the overall thickness is 102 mm. And here the application of piston parking. So for inside the wheel alignment, here the off-way truck. So this kind of a truck is made and assembled from the caterpillar. So this kind of off-way truck can carry the heavy loads up to 400 tons. So this will be mainly used in the steep and uneven grounds. So here that yellow part is called as a piston. This is a piston parking components which is hydraulically actuate both service and the retarding function. Retarding function in a sense, the movement of the vehicle has to be initially stopped to hold the position. It also works in both service and also in retarding function is same essence. The green color shows that the spring, which is an oil cooled spring, which is also hydraulically actuated with use of an oil. So when the friction disc gives a pressure to the piston parking, the secondary piston move towards the oil spring, so which is used to hold the wheel align. It is used to apply the brake with the use of the pressure. So here the oil cooled as well as the secondary piston and also the hydraulic pressure is a three type conception of level of position is using with respect to of the pressure, and it applies a brake. And this is about experimental design work. This material is a general of SG iron, which is made of the grade of SG 550/6, and the net weight is about 25.315 kg. And the mold material for the in production process, they were used in the silica sand as per the industry content. So totally it is an industrial based project. So they were using the mold material as a silica sand, and gating ratio they are maintaining with the pressurized gating is 1:1.5:0.8, but the general in a sense 1:2:1 is the pressurized gating ratio for the ductile material. So with respect to the gating ratio, we can also reduce the percentage of reducing the scrap level, and the mold box size is 110 into cross 840 into 550. 550 is nothing but two parting line will be separated which is 275 at the top and bottom. And this is a gating design calculation. So as per the industry follow the pressurized gating design for the area calculation, which is with respect to the sprue, runner and in-gate 1:1.5:0.8, and the area of the sprue, which can be calculated by using the formula of pi r square or pi d square by 4, and the area of the runner bar is area of the sprue into 1.5 times, and area of the in-gate will be showing with the area of the sprue into 0.8 percentage. This is a method 1, which is an existing method of gating design. The same design which is already been set up in the pattern match plate. With respect to the size, I am measuring each of the runner, sprue, in-gates as well as the feeder base and also the vent component size has been measured, and these kind of design which is used to design using the SolidWorks 3D model software, and this with respect to the process parameter and how much of the percentage of the composition, pouring temperature, pouring pressure, yield, weight percentage will be analyzing throughout the optimization techniques of the AutoCAD software of simulation software. And this is a gating calculation for existing gating system, and they were using with the method 1 of an existing method. The grading ratio is not at all a proper one, so they were used about 1:1.03 is to 0.765 with respect to the previously we have shown this kind of a gating system. So this is a general calculation for the sprue, runner bar and in-gate. Dia is about 50 mm because the match plate size is about 110, 840 into 275 and 275. With respect to the sprue size, and the machine molding is also capable of produce the sprue dia is about 50 mm. So this is about area calculation for the sprue. For the runner bar, the area of the sprue into 1.03 and the level with respect to that, and one runner bar is using the center part which is directly feeded with a straight line of the bar, which is called as a runner bar, and opposite to that of this is called as a in-gates. Two in-gates were using with respect to the height and width. This kind of a calculation has been made and tabulated by using for the gating system. Sprues around dia 50 mm, and so all dimensions are in mm, and height is 275 at the top. One sprue is using, runner bar is one number, so length is 162 and width is 33.7 and height is 57. In-gate 57 cross 75 cross 10, and feeder base is dia 184 cross 105 is height of the feeder base, and feeder neck is 80.42 cross 52 to feeder neck. Feeder type type is exothermic sleeve, which is exothermic sleeve will be using because it will create a it will liberate the heat up to the specific requirement of the heat requirement, but it will also enables the heat by liberating inside that. So since the feeder will have the liquefied metal inside the feeder, so if it is not at all cooled inside the mold cavity, so it will be taking from the exothermic sleeve. So vent of dia is 25 cross 275. Gating ratio is 1:1.03 is to 0.765, not attained as per the ratio. This gating design calculation is for method 1 and 2. So this is about the simulation result of method 1, where here the component is feeded into an AutoCAD software, and in the left side will be showing with the different of number of icons will be displayed. So for the ST550/6 we need to choose that PR light should be a major concern. So I'm clicking with that. Then processes for the green sand casting, and the level of the composition will be given as per the industry they will be using. So the composition has been entered. then no chills were present. So that is the orange color will be an exothermic sleeve which is feeder over the top of the feeder base, and this is an exothermic sleeve which improve the yield percentage and also reducing the fettling cost, better metal feeding and improve the directional solidification. Exothermic sleeve function is generally liberating the heat but up to the specific heat requirement of the riser, and also it limit the temperature loss of the molten metal inside the riser, thereby keeping the metal hotter and liquid longer. So if the component is not feeded up to the level of mold cavity, it will be taking from the riser. So the exothermic sleeve is all made up of an aluminum dross, which is an extracted after from the extraction of an aluminum, and also the some kind of the fibrous refractory lining material will be used, and also some binders will be there. And with respect to the potassium nitrate will be added, or some kind of an alumina, magnesia. So these kind of a binding techniques which is used for as a exothermic sleeve, and also it will be acted as a refractory lining because it should not be melted or tend to be an ash before the liquid metal of the temperatures around 1400 degrees Celsius. Then this is about the simulation result of method 1. So we checking the limit of the 0.01 percentage because the level of the shrinkage level is 1 by 100 times. So with that minimum level of 0.01 percentage, there should not be any red spots. The red spots indicates that shrinkage is present inside the cavity. Here the dia is about 140 mm, height is around 200. So here the reversing of the metal, liquid metal is reversing towards the cavity. So because of the solidification, the flow is incorrect because of the feeder height. So the sprue should be, and also the sprue should be placed at the center of the casting, and the yield of the casting is around 74.83 percentage. And simulation of method 2, the same design component, only the chill is placing. Steel chill I am using with respect to the 6 chill at the hollow circular ring. I am placing the chills at the bottom of the casting in order to reduce the shrinkage level. So this is about the simulation result. Since the shrinkage is observed not at all up to the minimum level of in the method 1, here the yield is obtained is 74.83, is the same as that of method 1, but the spots are taking place in between the two chills. So here between the two chills, metal is shrinking there. So the contraction takes place. Solidification is, the level of the shrinkage level is very high. So solidification is not attained properly, so there may be some kind of an porosity, or it may be a pinhole, blowhole will be presented over there. And this is a method 3. I am modifying the method with the gating design with respect to the gating ratio of 1:1.5:0.8, and this is about the general calculation as previously mentioned. And the sprue calculation is about a dia 50 and across 275. Here the runner bar is 4 runner bar using and 4 in-gates were using, and the center of sprue is placed at the center, and instead of the top feeder I am using the side feeder for the better flexibility to flow of the molten metal. And here about the different parameters I am using feeder with respect to the feeder neck. Then exothermic sleeve is 4 cross 4 inch sleeve. Exothermic sleeve is using for the method 3rd and 4th. Since these were placing with respect to the height is 140 mm for the feeder height, but there total is around 200 height is placed between the exothermic sleeve, and here the height is also reduced and the method is also been reduced. And this is about the simulation result. Since the shrinkage is observed but the yield obtained is 89.74 percentage. Why it is attaining the shrinkage at the feeder neck is due to the inflow of a material. So after that the mold box size and mesh size and the feeder height is, since it is reduced from 140 to 100, So with that handle, the simulation is already solidified, and this is about the result. That is, in cause of no shrinkage is observed at the yield, and yield is attained about 91.82%. So this method 4 is attaining the yield, and also the no defects is found. So this kind of the gating system can be incorporated in the production line for further processing. So, and also we can analyze the temperature with respect to the thermocouple analyzing inside the simulation software. I am slicing over the thickness up to the level of 60 mm. Below that, with respect to clicking the point at the center of the sprue, runner bar, and inside the cavity of the mold, and also the feeder neck and the riser, we can note the temperature with respect to how the cooling time with respect to the temperature is taking place. And this is about the simulation video which is recurring, and I will show us in the end the design of the spring sheet. And then second part is about the spring sheet component. This is about the top view, bottom view, and side view. With respect to the size, the spring sheet of the component, total thickness of the material is 75 mm. At the bottom there will be some cavity. The total cavity's height is about 40 mm. So the overall width, height, length has been shown with 166 cross 284 cross 118, and the thickness is about the width of this is 128 mm, and the thickness of the part is around 75 mm. So this is a real-time application of the spring sheet which is welded over the wheel, rear wheel axle. The spring sheet will be welded throughout the axle tube, where the leaf spring sit flat on the axle. It is securely molded on the axle to the leaf spring with the U-bolt. This is a real-time application. It's also being used in the heavy vehicle trucks. And this is about the experimental design work. Material is same that of which is previously as shown in the piston packing. Grade, this part number is 3277 ZC 364. This is for the general category of the pattern name. Then net weight is 19 kg. Same pressurized gating with respect to the ratio. Only the mold box size is very minimal. That's 660 cross 508 cross 400, which is a set of the parting line. Above 200 and below 200 mm will be taking place. This is about the general property of the rough casting. And here the method 1, this is not an existing product. This is a new product development component with a designing gating. So the part is fed into the simulation software, and the exothermic sleeve of dia 40 mm which is placed over the top of the mold, and the metal flow will be erased using the simulation software. Then after that, solidification will be taking place with respect to of the yield is about 87. So here heavy shrinkage is observed because metal flow is reversing. So the component with the feeder as well as to the component thickness, metal cavities, molten metal is not at all being sufficiently filled inside the cavity, so it is causing the heavy shrinkage. And simulation result of method 2, I am replacing the same center feeder with this 2 side riser because the metal is not at all exactly filling over the cavity. So placing of 2 risers of about dia 80 mm and height is 120 mm with a proper neck area for the feeding center part of the casting. And the total gross weight is around 36.48 kg and yield is 55%, and the heavy shrinkage is also been observed inside the casting, not as same as that the level of percentage of the heavy shrinkage when compared to the method 1. In method 3, the size of the riser is generally reduced here with the height of 120 mm, but here the height is 40 mm. Then 2-inch exothermic sleeve is placed at the center. Metal feeding is also not at all proper, but the yield is 70%. Shrinkage is also attained at 0.07%. So the gating calculation for the method 4 will be replacing with 1:1.5:0.8 with respect to the only with up to the method 1, 2, 3, trial and error method have been developed, but for the method 4, I am using respective to the gating calculation. With respect to this width, height, these are all changing, and also the change of the runner bar in gate and feeder. Runner bar 3, runner bar here used, and in gate 2 feeder is also 2. So this is a designed part which is made from which is designed from the SolidWorks, and this is about the pressurized gating ratio of 1:1.5:0.8 of the spring sheet component, and this is about the simulation result which is feeded into the simulation software. And after the solidification is attained, of the diameter is 80 mm and height is 135 mm, simulation result is observed to be failed. Shrinkage is also present with the casting yield is 57%. So next, what kind of the gating calculation can be done for the method 5 in order to reduce the level of defect, and also with respect to the yield percentage has to be increased. Here only the 50% of 57% of yield is observed, but here after the calculation for attaining the parameters of the gating design, this is a finalized method of method 5 with respect to two ingates and one runner bar is placing from the distance of 57 mm center of the sprue, and one side riser is using the design of the gating, and one chill of dia 75 mm is placed at the top, and the pressurized gating is maintained, and diameter of the sprue is 30 mm with a single ingate, and two runner bars are designed with the area calculation. And this is after which is get feeded into the simulation software. The level of the shrinkage is 0.07%. There is no more cause of the level of shrinkage at 0.01%. So this kind of method 5, after the trial and error method 5 is utilized as an inline production process, and the yield is also obtained to be 84.52%. So it is cause a good production process. And general properties for both cast component surround specified chemical composition ASTM of A 536 with respect to the ISO standard of 1083, which is similar to the 500/7. Here ST 550/6 is used. Carbon is around 3.2 to 3.8. Then after analyzing using the spectro, 3.43 actually maintaining. Carbon, silicon, manganese, sulfur, phosphor, chromium, nickel and magnesium 0.04. Since it is an ST, magnesium is using, and nodularity 90%, pure light maximum 50, but it is attaining 70. Ferrite and carbide, no more carbides will be placing. Then hardness is 187 to 255, but the 242 is Brinell value of W is nothing but the Wolfram tungsten carbide ball. Tensile is 552 megapascal and 379 tensile of megapascal, and elongation is 6%. Then this is about chemical analyzing. The metal analyzer, that is AL360 metal analyzer for the optical emission spectroscopy, is used to analyze the composition of the material, and which is tabulated, and result of microstructural analysis is done using the Koiba-Jenner metallurgical microscope to identify the phase present in that. When the melt number of C65112 was made with a nodular content of 90% and perlite is 70, ferrite is 30% and carbide is null level, the polishing is done using the dispolishing machine, and the reagent of 2% of nitrile solution is used as nothing but the 2% of nitric acid and ethyl alcohol of 98%, which is etched over the material, magnified at the 200x, shows the bullseye kind of face present in the cast iron, and which is nothing but the black color faces are called as a perlite, which is very strong and fine compared with the ferrite, that white faces are ferrite, and center part which is called as nodules. This is about the microstructure of the SG 550/6, and the hardness test we using the Zwick hardness tester load is about 3000 kgf and the diameter of the ball is 10 mm. Dwell time is 10 to 15 minutes and the hardness is taking with the average value of 3 specimens at the location, and hardness value of the SG550/6 is getting, and with the average hardness of 4 to 43, and this is about the result of the tensile strength. The bar of SG550/6 for the tensile specimen is made, and this is the diameter of the bar is 25 mm, which is held to placed inside the UTM machine. After that, the elongation will taking place at the 693%, which is around 7%. After that, tensile graph is shown. With respect to the tensile is around 593, yield is 473, and elongation is 7.49% for the SGN. And the simulation videos with respect to the conclusion, only the pressurized gating is using for both the piston parking as well as the spring sheet component is 1:1.5:0.8, and using the CAD software and simulation software, optimizing technique has been done. And the same with respect to of the ASTM A536, the material similar to that of periodic matrix nodularity, and also the tensile hardness is also been attaining by using the optimization technique of the simulation software using of an AutoCAD X1. Designing optimization, we can reduce the time as well as the consumption of the material, of the raw material. Either the scrap percentage is also been reduced, and the quality of the material is been very high, and yield percentage also been very high. And this is about the reference, and thank you. Then with respect to this, I will be showing a video which is to be taking place after the percentage, and with the level, what kind of the phases of the, I will be showing with the spring sheet of videos, which kind shows that how the solidification level will be taking place from the phases towards the material. And we can conclude by saying that using different sources will be available, but only with the cause of simulation and optimizing technique we can reduce the level. So this is about the solidification will be taking place due to the flow of material. This is nothing but the color changing will be taking place with respect to the temperature, which is shown as the color ranges at the temperature to the top of the amount. The current time and the volume solidified will also be taking place with respect to the percentage. The color code, that is white with range of the temperature is 1420, and with respect to the color indication towards the violet black, this cause a temperature at 0, and after the cooling temperature will be taking place. So this is an overall objectives of which is used from the optimization technique, and thank you.